Good evening, everyone. Welcome to the first audience tutorial session of the NPTEL course, Physical and Electrochemical Characterization Techniques in Chemical Engineering. So, this is a course offered by Professor Tamal Banerjee of the IIT Guwahati. So, in this sessions, following like there will be such kind of sessions in every upcoming weeks. So here we'll be discussing like whatever like Professor Banerjee has already been discussed in his class and some of the few example questions that he might be asking in the assignments or the kind of question that has been asked in the quizzes. So by this kind of a tutorial session, you guys will be able to get a better idea on how to do the tutorial sessions and the wishes of this corresponding NPTEL course. So, so let me just start my share my slides. Yep. I hope you guys can see. So, welcome to the first online tutorial sessions of the physical and electrochemical characterization techniques in chemical engineering. So today the date is 7 February 2023. So myself, Rahul R. I'm a Prime Minister Research Fellow at the Department of Physics, IIT Kharagpur. So I'll be handling this online tutorial session. So if you have any queries, you can contact me or on the next classes. So this is a regular link, and the classes would be there on a regular basis on the upcoming weeks. So upcoming 8 weeks. So yeah. So so in the first lectures. The first week lectures were mainly, so today we'll be discussing on the first week lectures, and that are the introductory lectures on the electrochemical and physical characterization techniques in the chemical engineering. So one of the first thing that we basically discussed in this lecture was the different types of material characterization techniques that are generally being used in the research. So yeah, so there are plenty of research, material research options that are available. So of that, some of the major uh, characterization techniques are, say, XRD. XRD is a very common technique that has been used in the material science to uh, understand the about the crystal structure and the crystalline quality of the materials. So XRD stands for X-ray uh, diffraction, and it is mainly used to understand about the crystalline structure, which gives us the information about maybe say lattice strains, and other corresponding parameters corresponding to the crystal structure. And the other technique that can be exploited or using this XRD technique is about the quality of the crystal. So like the crystalline quality. Crystalline case. So this uh, this technique would actually give me information about the purity content, like if there are any purities present in the material, like if the phase formation is proper. Also, all those information can be obtained using an XRD technique. So this is a very powerful technique that is very regularly used by the material research scientists on a daily basis. And the other commonly used technique is SEM. SEM stands for scanning electron microscopy. So basically, yeah, going further beyond this, I can moreover like broadly classify this again. Base research technique can be, yeah, some more broadly be classified into what I say techniques. Techniques can be classified into say one physical or say chemical and maybe electrochemical. Physical characterization as I said, gives you an idea about the physical behaviors of the like the how the structure is, like XRD, SEM, TEM, etc. And there is this chemical characterization techniques where you get the information about the chemical composition of the material. So here it will be like XPS, XSF, etc. And there are electrochemical techniques like uh, charge discharge, cyclic voltammetry, EIS, which give us information about the electrochemical. So these are the few. One second. Yeah. Okay. Yeah. So now I can see if someone joins the meeting. So yeah, sorry for the interruption. So yeah, what I was saying is that the characterization techniques, so material characterization techniques can be basically one, physical, second, chemical, or maybe the electrochemical. So as I was saying, these physical techniques can be basically XRD, SEM, TEM, etc. The chemical, where we get the idea of the chemical composition of the material, that can be, for example, XPS, XRF, etc. And electrochemical techniques can be basically cyclic voltammetry, cyclic voltammetry, voltammetry, charge discharge, electrochemical impedance spectroscopy. Most of these techniques would be discussed in a very detailed manner in the further lectures. So each of this topic would in itself be a topic for discussion, and everything would be discussed in a proper manner so that you, the students or the listeners who you are participating in these lectures can get a proper understanding of what each of these techniques are. So now for an introductory part, let us just stop here by understanding that there are basically three kinds of characterization techniques. One is physical, which include techniques like XRD, SEM, TEM, etc. The other one is chemical, which gives us information about the chemical composition of the materials. So that includes chemical characterization techniques like XPS, XRF, etc. And there are other techniques like electrochemical techniques, which gives us the information about how the material would react to an incoming voltage or current. So these are the basic three techniques. Now let's go beyond. And the next question is, what are crystalline and amorphous materials? So to start with material, we have to see what are the basic two kinds of material that we can see. So they are either crystalline or amorphous, and there are many other classification also. But in general, we can stick to the very fundamental two kinds of classification. One is crystalline, and other one is amorphous. In crystalline, the materials have a proper repeating and ordering arrangement of atoms, and there is a proper pattern in a total 3 dimensions. These are very repeating patterns, and whereas if we consider this amorphous material, there is not that kind of a proper material. For example, you can see from this figure, this crystalline has a proper arrangement. Say I call 1, 2, 3, 4, 5, 6. So there is a proper arrangement of it, and corresponding to 1 there is here, and there is an atom here. There's considering 2, there's atom here, an atom here. So there is a very proper arrangement of atoms on a very regular basis. And see, there is a, but if you go for this amorphous, you can see that yeah, there are atoms, but the arrangement of atoms are not regular. So there is 1 here, but there is no atom corresponding to here. So there is a gap here. You can see there is a white space here. So here the arrangement is not proper. So this is an ordered arrangement, whereas this is a, there is no ordering here. Ordering here. So this is a crystalline material and this is an amorphous material. So if we do an XRD plot for a crystalline material, we get proper peaks. Like ideally we should get very sharp peaks, like should be kind of a line. Sorry for my building. So it should be kind of a very straight line. Whereas in amorphous materials, the XRD peak would be kind of there won't be any such kind of proper identifiable peaks, rather than it is a kind of diffusing manner. So once again, there are the basic and a very fundamental manner. We can say material can be of 2 types. One is crystalline, and in crystalline materials there is a proper ordering, and the other one is amorphous. Where in amorphous material there is no proper ordering of the atoms. Atoms. Okay. Now I think we can move on to our next question. What are nanomaterials? So nanomaterials are one of the very fundamental thing that material scientists deal on a very daily basis. We play with these nanomaterials to get information or to make very use of them to for various practical applications ranging from pharmaceuticals to energy storage devices. So what is a nanomaterial? Nanomaterial is a material so whose either any one of its 3 dimensions, the size of that dimension is under few nanometer, or more rather we can say, let us say we have 3 dimensions, say x, y, and z. If any one of this dimension, the value is in the range 1 to 100 nanometer, then we can call this a material. So this is a material. So this is a material. Material is having this dimension. And if any one of its dimension, either length, breadth, or height, is in the range 1 to 100 nanometer, then we can call this a nano material. So obviously we can see that we can classify this into different types. So here we can see from this figure, the figure A would give you an idea about this direction. So this is X and this is Z and this is Y. Now, if all the 3 dimensions are greater than 100 nanometers, so you can see from this figure, this is a bulk material. This is a micro material or macro material, anything. So this is not, I can just say that this is not a nanomaterial as all the 3 dimensions are greater than 100 nanometers. Now, if at least 2 dimensions are greater than 100 nanometers, greater than 100 nanometer, while the third one, say here the Z is less than 100 nanometers, then this is a 2D structure. This is a 2D nanomaterial. No material. An example for 2D nanomaterial is graphene. It's a very well studied material. Graphene, it has used in a very wide range of applications. And yeah, to go forward, and now we have see this is greater than 100 nanometer. This is greater than 100 nanometer, and this is less than 100 nanometer. So yeah, now if what we do is if we make a material, if in that material, two of its dimensions is less than 100 nanometer, is less than 100 nanometer, then that is a 1D structure. It's a 1D structure. So an example for carbon 1D structure is um, an example for 1D material. An example for 1D material is carbon nanotubes. So the carbon nanotubes is also a very well studied material nowadays, and they are also being used in a wide range of applications, and they are being very much exploited for various applications. Now, if we make the other dimensions like in 2D material, in a bulk material, all the dimensions are greater than 100 nanometers. In 2D material, only one direction has its dimension less than 100 nanometer and the other two are greater than 100 nanometer. In a 1D structure, uh, except one or the other directions have their dimension less than 100 nanometer, whereas one of its dimension would be greater than 100 nanometer. And in a zero dimensional structure, that is 0D structure, all the dimensions x, y, and z have its size less than 100 nanometer. So this is called a 0D structure, and an example for this are quantum dots. Quantum dots. For example, there are this carbon quantum dot CQDs, quantum dot that has been application in many aspects from sensors to various fields. So this is a very fundamental understanding of nanomaterial. So once again, nanomaterial is a material where one of its dimension is less in the range of 1 to 100 nanometer. It can be basically classified into the 2D structures, 1D structure, or 0D structures. Going forward, now, what is the key difference between alloys and intermetallic compounds? So, in the material science, the other two aspects that have been regularly discussed are one, alloys. So, alloys is a mixture of metals. Alloy is a mixture of metals, and the other one is an intermetallic compounds. Intermetallic compounds. So basically, intermetallic compounds is different from alloys, where in the aspect that it is composed of two or more metallic elements, and in alloys it is a homogeneous mixture, whereas in intermetallic compounds there is a proper stoichiometric composition of the materials. So, for example, in intermetallic compound, if there are two kinds of materials, say X and Y, they will be mixed in a proper stoichiometrically manner. So there will another difference another difference between these alloys and intermetallic compounds is that in alloys the crystalline structure may not be well arranged, whereas in a intermetallic compound we can have a proper arrangement of this proper arrangement of the atoms or these compounds within the structure. So these are the two different kinds of materials that material scientists deal with, and they have their own uses. And yeah, so going forward, what are ceramics? Ceramics is a class of material made by heating natural clay or other materials to very high temperature. So the key thing to remember is the high temperature. So here the materials would be heated, some kind of material, for example, clay, would be heated to a very high temperature, and thus they become brittle. They are basically non-conductive in nature, to both electrical and thermal. And thermal, they are generally hard. So these are the basic ideas of the ceramics. So these have a very profound uses in different fields, like in ceramics Or ceramic coated. Now you can see even the mobile phones come with the ceramic coatings on their back because they are hard. So this is also one of the most studied material. Now polymers. So polymer is a is an arrangement of monomers. So there is something called monomers. Monomers is a chemical compound made. So this is a chemical. So if that is, say, A, B, this is a chemical compound. And if this is arranged to n times, so there is a regular arrangement or there is a continuous arrangement of this monomer. So this is called a monomer. And when this monomer is connected to say n number, then it forms a polymer. So polymers are also being very well studied material nowadays. Polymers have been used in batteries as they are uses in flexible devices. They have been used in drug discovery, etc. So this is a very well studied. So basically, polymers are a large molecules made up of repeating units called monomers. They are versatile material and that can be engineered to have wide variety of uses. And yeah, their strength and everything can be very much tuned. And these polymers can be naturally obtained or that can be synthetic also. So they are naturally obtained naturally obtained polymers and synthetic polymers. So these have their own uses and they have been used on wide variety of applications. One, yeah. Now going further, the other type of materials that materials scientists deal with are semiconductors. So semiconductor is a class of material that is between conductors and insulators. So basically, for a metal, if we consider the energy band gap diagram, you can see that the energy band diagram, you can see that the conduction band, the blue color represents the conduction band, sorry, the valence band, conduction band, and this represents the valence band, and there is a clean overlap between the conduction band and the valence band. So this generally refers to as metals. Now, if we go to insulators, there is a huge band gap, and electrons, it is impossible for electrons to jump from their valence band to their conduction band. And now there are other class of materials where this band gap is not that high, but there is a band gap so that if given proper potential, electrons from the valence band can mm, electrons in the valence band can jump to the conduction band once proper energy is provided. So this band gap can be tuned by doping, and this is been a very fundamental for our electronic revolution. Electronic revolution. So semiconductors are the basic for all the electronics that we see. So either we top, so this can be N-type or P-type semiconductor, depending upon the kind of doping we do upon them. So these two, so this is another very regularly studied material. Now let us go to other question. So what are the major type of energy storage technologies available? So energy storage technology, so there are many different technologies. Like if we can go, like there can be mechanical energy storage technology, there can be thermal, chemical, chemical, and there can be um uh, yeah, basically there are many there can be many different kinds of electrolysis. So the major one that we discuss here is the electrochemical energy storage technologies, which mainly include fuel cells, batteries, and capacitors. Or there is also a class called super capacitor. So these are the major electrochemical storage that in this upcoming lectures also we may focus a little bit upon these electrochemical storage systems, and these are the major electrochemical storage technologies: the fuel cells, batteries, capacitors, and the supercapacitors. Okay, now let's move on to the next question. What is a Ragon plot? So this is a very fundamental plot that would come across in the research of batteries or any other energy storage devices. So Ragon plot is a plot, it's a two-dimensional plot with energy density on the x-axis, and the power density on the x-axis. This is x-axis and this is our y-axis. So this plot would provide us information about how efficient our energy storage technology is. Efficient in the sense how well it can store energy and how well it can deliver that energy for a particular use. So this is much more a sophisticated plot. So here we can see the y-axis to be energy density with its unit watt per kilogram, um, and we can have power density, which is watt. Okay. So basically by plotting this, we can get an idea of how efficient our energy storage device is. So if we consider just one point over this, we can get an idea about like how long this device can deliver a certain amount of power. So we have, say, consider this point, and this will tell me that this device would give me this much x amount of power for y amount of time. So this is the basic inference that one can get from a Ragon plot, and this is basically very powerful plot that is used in the battery or supercapacitor or any other energy storage devices to compare the performance with other versus other other technologies. Maybe you develop a battery with, say, X as the anode material. Yeah, we will see what is an anode and all. So X as an anode material, and there is another already done research with Y as an anode material. Then you can compare your device with this by doing this by plotting a Ragon plot with the energy density and power densities, and you can see how your device, say, overperform your for past research. So the ideal way to go forward is we need to get into this area with a very high power density as well as very high energy density. So you can see that capacitors are having very high power density, but they lack the energy density, which implies that capacitors can deliver a huge amount of power at a very short time, but the amount of power that capacitors can actually store is very less. Whereas you can see the fuel cell, they have a very high energy density, but they lack the power density, which means that you can store a huge amount of energy in a fuel cell, but the rate at which you can extract the energy out of a fuel cell is very slow. For example, in a certain case, you may need to extract energy so fast. For example, if you're accelerating your electric vehicle, so you need a high amount of power at a very short amount of time. So there you have to go for a very high power density storage device. And there are situations where you need to have a huge amount of energy stored, so that can last for and where the lifetime is much more better. So those so according to our need, so actually we should aim to go forward in a this direction with very high power density and very high energy intensity. Okay, now let's go forward. So what is the major difference between batteries and supercapacitors? So batteries and supercapacitors are the two kinds of devices that two kinds of energy storage devices that uh, that is currently available in the market. These are very commonly used devices also. So yeah, there are other devices, but of those, batteries and supercapacitors are not very common. So batteries, yeah, and supercapacitor differ on the basis of their charge storage mechanism. Charge storage mechanism. First difference comes in the charge storage mechanism. In batteries, charge storage mechanism actually occurs due to redox reactions happening inside the material, whereas in a supercapacitor, charge storage mechanism happens due to the arrangement of positive and negative ions. So if you have an electrode, yeah, let us now continue. So in a supercapacitor, instead of storing the charge via redox reactions, here the charge like the counter ions, say if this is a positive electrode, the counter ion negative ions would be arranged in a regular manner, and this separation of charges at a very smaller distance would cause this in a charge storage. So these are the basic diagrams of say an electrical double die capacitor and a lithium ion capacitor. So as we are going to discuss in the upcoming slide, like supercapacitor can be of different types, mainly three types according to their charge storage mechanism. So one of it is the electrical double die capacitor. So basically this is a schematic diagram showing the difference between a supercapacitor and a battery. Now now let's discuss the next question. Name a few techniques that are beyond lithium for storing the energy. So currently one of the most discussed and most widely used technique to store energy is the lithium batteries, lithium based batteries, where the charge storage is mainly occurred uh, by this lithium ion. But we have been, due to many geopolitical and due to this availability problem of this lithium, and lithium mining of lithium is very polluting. So there are many factors that are forcing the market to go for technologies that are beyond lithium. And some of the very promising technologies are, say, sodium ion batteries, and people are researching on aluminum ion batteries, aluminum ion batteries, and there are potassium ion, calcium ion, magnesium ion. So the people are trying to go to get an better energy storage devices beyond lithium, and some of them mainly obtained energy storage device promising us. You can see from these papers, so all these are published on Nature. So this is a sodium based, and this is aluminum based battery, and this is a potassium ion based batteries. So these are the few technologies that are promised to be a beyond lithium energy storage technologies. Okay. Now let us go to the next question. What are supercapacitors and what are their basic classification? Yeah, as I said earlier, supercapacitor is a kind of energy storage technology, where charges are stored by means of charge separation. So here we will have an electrode, and there will be electrolyte. So there will be this electrolyte, and there will be this other electrode. So here what happens is that if this electrode say be positive or negative, so when it is charged, the counter ions present in this electrolyte would come closer to this electrode, and this charge separation basically stores charge. So this is a very fundamental way of explaining a supercapacitor is. And to go further, the supercapacitor can be classified into basically three. The first one is electrical double layer capacitor, which is just as I mentioned. The other one is pseudocapacitor. Here what happens is that the charge storation occurs due to the Faradic reactions happening at the electrode surface. So there can be Faradic reaction happening between this electrode material and the ions that are coming to this surface. So that this reaction will cause charge storage in this kind of supercapacitor. The other one is a hybrid supercapacitor, which is a combination of electrical double layer supercapacitor and pseudocapacitor. If one electrode is of electrical double layer type behavior and the other electrode is of pseudocapacity behavior, then this kind of a supercapacitor is called a hybrid supercapacitor. And based on the device configuration, there can be symmetric and asymmetric supercapacitor. If the two materials on the used on the both anode and cathode are same, then that is a symmetric supercapacitor. And if two materials used are different, then that is an asymmetric supercapacitor. Now let's go to the next question. So what is the technique that is used to analyze the surface area and pore size? Yeah, so the technique that is used to understand the surface area and pore size is BET. BET is a very well studied technique, and BET stands for Brock, Emmet, Teller technology. So these are the three named after three scientists who basically worked on the theory behind this. So this is a technique that is generally used to understand the surface area and pore size in a material. So we'll be discussing about BET in a very detailed manner in upcoming lectures. So at that point, we'll be discussing more about BET, and possibly we will do few questions regarding these techniques. Now, the next question is, the dash is used in the particle size analyzer to calculate the particle size distribution. Okay, so particle size analyzer is another commonly used technique in material science research, which actually give us an idea about the size of the size of the particles in the material. So basically, in a particle size analyzer, we do this calculation by actually calculating something called the autocorrelation function. Autocorrelation function. So the autocorrelation function is used in the particle analyzer to calculate the particle size distribution. So autocorrelation function is a statistical tool that is used in the particle size analysis to quantify the what we say. So we'll basically quantify the similarity between the signal and its delayed signal. So we'll be discussing more about this in the future. So basically, all we need to know now is we depend on autocorrelation function to determine the particle size distribution in a particle size analyzer. Okay, so we can go forward. Yeah, now there's another technique that is widely used in the material science. It is called the thermogravimetric analysis. So thermogravimetric analysis, it measures dash as a function of dash. So this is a regular test that is performed to see if there is any change in mass as a function of temperature. So change in the mass of a material as a function of temperature. Yeah, just a second. Yeah, as a function of yeah, here what we basically do is we measure the change in the mass of a material as a function of temperature. So this will give us an idea on how your system, your material system is stable with temperature. So this is a very commonly used technique in this material research. Now, the next question is chemisorption generally measures dash and dash. First one that chemisorption measures is metal dispersion, and the other one is the active metal area. So metal dispersion generally refers to the ratio of number of surface atoms to the number of total atoms. And active metal area defines the area of the material that are chemically reactive. Area of the material, yeah, that is chemically reactive. So this is what chemisorption is. Now to go forward, dash is a technique that can be used to calculate the quantitative determination of transition metal ions and the band gap of a material. So yeah, this is another regularly used techniques in the material scientist, and this is regularly used to determine the band gap of your material. Yeah, so the answer for this is UV visible spectroscopy. So in UV visible spectroscopy, which is spectroscopy that uses UV and part of visible light to do this characterization, and then this will give us a result to see what the band gap say, maybe 3.1 electron volt. So if you're working on CR2, you're working on CR2 3, and you perform this UV visible on this. So this will give us a result showing that the band gap of this CR2 yeah, say that can be around 3 to 3.4. So let me say 3 electron volt. So these kinds of information can be this techniques has been used to regularly extract information about band gap using the UV visible spectroscopy. And the other techniques are Raman spectroscopy, FTIR spectroscopy, and that have their own uses. Okay, now to go forward. Yeah, now let us go forward. The dash technique can be used to study the molecular structures and interaction of metal oxides. So yeah, so this is another, yeah, this is some more complicated technique. Whereas UV visible, you can have a portable device. Portable in the sense comparing to a Raman, UV visibles are comparatively portable devices. And these techniques, yeah, the answer is of course Raman spectroscopy. So Raman spectroscopy is a technique that is used to study the molecular structure and interaction of metal oxide. So this gives us information about how the molecules, what is the structure of a molecule, and other what is the what and the interaction of it with the other metal oxides. Okay, now to go forward, we can discuss about the different electroscopic techniques. So yeah, the commonly used electroscopic techniques are first one, X-ray, photon or photoelectron, photon spectroscopy. X-ray photon spectroscopy measures the energy of electrons that are emitted from a surface of a sample when it is being bombarded with the X-rays. The energy of these X-rays is a characteristic of the element present in the sample. So basically we get, and so once we have a material and if we bombard X-ray with X-ray with this, then we can get information about the composition of this material in this surface atom, first surface of this material. So there is a limit to which this X-ray can penetrate within this material. So say this X-ray is penetrated to say X nanometers, then this is basically called as the surface atoms. So we can get an information about how this, what are the composition of this surface, like what are the elements that are actually present in this surface. Okay, so this is basically used to study the surface chemical composition. Okay, the other technique that is being regularly used is X-ray fluorescence spectroscopy, it is called XRF. This X-ray fluorescence spectroscopy. So this is in a way kind of similar to XPS, but here we deal with the bulk material. XRF, in XRF, instead of just getting information about the surface, we can get information about the bulk. So actually here we can know what is the bulk material made of. How much is the how much like each material, like what is the composition of this bulk material. In XPS, for example, it is generally used, say you have a material, say AX. Okay, so suppose this A can be of, can have different, can exist in different oxidation states, say A3 plus or A4 plus. So in your material, this AX compound, the A can exist in different composition, and you expect a particular phenomenon or particular result of a chemical. For example, if you're making a battery and you're getting some particular result, and you may think that that is particularly due to the presence of this A3 plus ions. So you expect your result to be because of the presence of a larger A3 plus ions in your material. Then you can do an XPS and you can get an idea of the ratio of A3 plus to A4 plus, and that is basically the chemical composition. Now, if you're doing a XRF study, so this on the surface. So if you're doing an XRF study, instead of getting information about the surface, you get information about the bulk. So when you need to, so in batteries, maybe you may not be interested to know about what actually the bulk of the electrode material, but you need to see how the surface of this electrode material interacts with the electrolyte ions present. So this is electrode, and you are not worried, like you know this in a battery, basically the electrolyte ions will get intercalated into this electrode. So, and you are hoping that this intercalation may not go deep into this electrode, but rather in the near surface of this electrode. So to get all those details, you can perform this XPS study to see what is actually the composition of this surface, and see how that is actually present, like what is the actual chemical composition. Yeah, that is X-ray and XRF. And one of the other commonly used technique is AES, which is Auger electron, Auger electron spectroscopy. This is a technique which measures the kinetic energy of electrons that is actually ejected from the material surface as a result of this inner shell ionization. So when so mm, if you're having an atom, so let us roughly assume this as an atom, and this X-ray may knock down one of its inner shell electron and ionizes it, and this may again transfer its energy to some other electron present in another shell, and again that will come out. So calculating this energy of this outgoing electron, we can get we can do this Auger electron spectroscopy. So basically it works on this about this Auger electrons. And yeah, the basic information that can be obtained from this is the composition in the bulk form and give of the entire sample. So this will also give us information about the bulk of the material. So once again, summarizing whatever I have said, there are, to answer to these questions, the three electron spectroscopy techniques are: first one, XPS, it stands for X-ray photoelectron spectroscopy, and the other one is XRF, which stands for X-ray fluorescence spectroscopy, and the other one is Auger electrospectroscopy. So these are the basically XPS is used for to understand the chemical composition of the surface, whereas other two techniques can be used to see about the chemical composition of the bulk structure. All these techniques would be discussed in a very detailed manner in upcoming lectures. So yeah, the following NPTEL course has dedicated lectures for each of these techniques, where you can get a fairly good understanding of what these techniques are. So here for today's lecture, the only thing we need to worry is to know what are these three different spectroscopy techniques. All their workings and the theory behind this would be explained in the upcoming lectures, and a proper tutorial for dedicated to these techniques would be taken in the further sessions. Now, the dash parameter is measured in a NMR spectroscopy. In NMR spectroscopy, we basically deal with the chemical shift happening. So in NMR spectroscopy, the chemical shift is used to identify the type of nucleus that is being observed, and it determines the composition of the molecule. So basically it is also used to see the composition of the molecule, and the chemical shift here can also provide information about the change in the environment of the nucleus. Like when there is a change in temperature, pressure, or any other chemical groups, we can see how these things affect the chemical reactions and the process. So yeah, basically this chemical shift is expressed in terms of parts per million ppm, and this basically chemical shift in NMR spectroscopy measures of the magnetic field experienced by the nucleus relative to a reference component. So basically in NMR spectroscopy we use TMS, which stands for tetramethylsilane, which is a compound. We see how the magnetic basically NMR is nuclear magnetic resonance. We measure the magnetic field experienced by a nucleus relative to this particular compound. So these techniques will also give us information about the chemical composition. So yeah, this technique, nuclear magnetic personas. So this is yet another techniques that we would discuss in a very great detail on the upcoming lecture. So to answer to this question is that the chemical shape is the parameter that is measured in NMR spectroscopy. So we measure chemical shape to understand what is the chemical composition of the tea. Now, yeah, we have already discussed this. NMR spectroscopy is used, basically used to determine. So I can keep on like every technique can be used to determine multiple facts like NMR spectroscopy. As I said, we can analysis the mixtures, analysis about the mixture, can analysis about the quality of this presence of impurities or other quality of this material, and you can also do this for structure determination. Structure determination basically means that we can determine the molecular structure of organic or inorganic compounds, including the position of hydrogen, carbon, nitrogen, etc. in the molecule. And we can do characterization of the dynamic process, where the NMR spectroscopy can use to study the exchange reaction, molecular rotations, tumbling, etc. On a time-dependent basis. So we can see how the molecules actually move, or we can actually determine the dynamics of a molecule using NMR spectroscopy. So to answer this question, we can say that an NMR microscopy can be used to analysis, determine the quality of the material, what is the structure, dynamics of the material. We can analyze the mixture, the material, etc. Okay. Now to go forward, we can deal with this. What does the SEM and TEM images show? So basically, the SEM is used to get information about the surface morphology, or a topology of the material, whereas TEM is used to study the internal structures. So SEM stands for scanning electron microscopy, or TEM stands for transmission electron microscopy. So you can see from these figures, this corresponds to SEM images, and these are few TEM images. And similarly, this is SEM, and this is TEM, and yeah, these both are SEM. So this data has been taken from these specific publications, and you can see we can visualize this nanoscale world or the micro world with a very good resolution using these techniques. So here we can see how the atoms are arranged on the surface. Like this basically gives you how the surface actually look like. So you can see that there are a specific surface. For example, you consider this from outside or from SEM image, we can see there is a bulk material, and the size of this is 500 nanometers. See, this much is a 500 nanometer material, but we doesn't know how this thing has what is the internal structure of this material. Or say, take an example of this. From here, we cannot say how does the internal pattern of this image actually look like. So if you go for a TEM image here, then we can get an information about how the internal structure of this image actually look like. So in nowadays in this in all the fields, people have been working on tuning the morphology to get various results. Tuning the morphology to get, for example, if you consider in case of energy storage technologies, energy storage, tuning the morphology means tuning the morphology would corresponding to tuning the accessible surface area. So once if a material has a higher surface area, that means that the probably the energy storage capability of the material will also increase. So people have been working on different structures like hollow that can be very evidently seen from these images. You can see here the structure is a bulk material. From outside with just the same image, we cannot see how the internal structure actually look like, but you can see actually it is a hollow inside. So these kinds of material would give extra surface, for the ions to interact and thus gives us a better energy storage area. So as you can see, it's the same from this image, which is also a hollow structure inside, and here also we can see a hollow. Here in SEM, we can see there is a slight opening here, but how the internal is actually obtained by the temp images. So thus we can say that SEM images actually gives us the topology or the surface morphology of the material, whereas the STEM images shows us the internal structure of the material. So you can see there are various structures that are actually possible to synthesis, which gives us a better result in various applications. So all these things have been used for energy storage technologies. And you can see this actually look like a cactus morphology with surface protrusion like this. And this would give extra space for charge storage. And this can also act as proper channeling for the ions to pass through. So all this playing with this morphology would actually increases the performance of different materials. And you can also see from this, which gives us a rose-like structure. You can so, and yeah, there are different. This is also partially hollow-like structure, and this is a plate-like structures. So all playing in the nano structures, this can be imaged with SEM and TEMP, and these images would gives us information about how the structure actually look like in the nano or maybe in the micro scale. And these structures have huge impacts on their performance or various applications. These structures can also have their applications in sensors, and yeah, this basically tuning these surfaces would gives us more surface area, and more surface area means more accessible area for elements to interact with, and thus gives us a better performance in various applications. Now let us go forward to understand the working voltage window of a supercapacitor. So as I mentioned in the earlier slides, there are different the basic characterization techniques in material science can be of three types. The first one is physical, second one is chemical, and third one is electrochemical. So electrochemical kinds of electrochemical analysis techniques is widely used to understand the working of electrical storage devices like supercapacitors, batteries, etc. So one of the major parameters that comes in a supercapacitor is its working voltage window. Working voltage window. This determines the energy density capability of the thus fabricated supercapacitor. So this working voltage window is generally calculated using a technique called cyclic voltammetry, and this is also known as CV. So these are the basic electrochemical. These are the basic electrochemical characterization techniques. Electrochemical characterization techniques generally used in material science: linear voltammetry, cyclic voltammetry, charge galvanostatic charge discharge, and electrochemical impedance spectroscopy, which is also known as EIS. So yeah, so out of this, cyclic voltammetry CV is generally used to measure the working voltage window in a supercapacitor. The working voltage window um, depends on the electrode material. This is an electrode material. Electrode material, and also it depends on the here electrolyte. So a particular kind of electrode material would be having a particular type of voltage window in a particular amount of electrolyte. So if you are having a electron material, say molybdenum sulfate MOS2, that is being dipped on a 3 molar KOH, for example, that would have a particular working voltage window, and that can be measured using cyclic voltammetry, which is also called the CV. Okay, now let's move on to the next question. What does EIS measures? EIS stands for electrochemical impedance spectroscopy. EIS, electrochemical impedance spectroscopy, and electrochemical impedance spectroscopy basically measures the resistance to the electric current within the structure, within the device. So if we have a battery cell, and if we need to know about what is the internal resistance of that battery material, then we can go for this EIS techniques, which gives us information about the resistance. Basically, when we talk in for AC current, it basically refers resistance by impedance of that cell for the external for the AC current that is flowing through this device. Now, the last question that we'll probably discuss today is dash are defined as the material that contains a mixture of two or more phases that are chemically different or separated by an interface. So the answer to this are composites. So composite, for example, if you're going for a composite that is graphene, MOS2 composite. So here we are having we will be having two materials. One is graphene and other one is MOS2. So this can be visualized possibly in this way, with this being graphene, regularly arranged array of carbon atoms. So this being graphene. So, and there will be a layer of molybdenum sulfate here. So this would be molybdenum sulfate. So this is graphene and this is MOS2. So these two are not forming any kind of chemical bonding with each other, but rather they are sitting in a very closed manner. So these kinds of mixture of two components are called composites. And these have many good applications. For example, MOS2 can MOS2 have generally lower conductivity, lower electrical conductivity, but when it is combined with graphene, which generally has a very higher conductivity, can in general increase the total conductivity of this whole material. Total conductivity can be increased. So in similar manner, there are different composites that are being synthesized in a very tailored fashion for different kinds of applications. So yeah, basically these are the questions that I would like to discuss today for this introductory course. And yeah, let me again just go back to the questions and let us discuss these questions once again from first. I'll just go from in a faster manner, just once again just analyze what we have already learned. So yeah, so in this course we will be going to learn about different techniques techniques the techniques in the sense experimental techniques that is used for characterization in material in chemical engineering, but this has a very huge application in material science, physics, people in basic engineering, physics, chemistry, etc. Material science, people from physics background, people from chemistry background. Yeah, all these people can use these different techniques. So the first question what we discussed today is basically what are the types of material characterization techniques that are generally used in a material research, and that can be basically divided into three. The first is physical characterization techniques. The other one is chemical characterization techniques. Last one is electrochemical characterization techniques. Physical characterization techniques give us the information about the physical structures or the physical aspects of the material, like their crystalline size, their crystalline like stress in the crystal, strain in the crystal, or the impurity presence of impurities in the material, etc. So this image and what is the morphology of the system, all this image, information can be obtained through physical characterization techniques, and some of the examples for physical characterization techniques are XRD, SEM, TEM, etc. Now, if we need to know information about the chemical composition of the material, then we need to go for these chemical characterization techniques. And some of the very commonly used chemical characterization techniques are XPS, XRF, and we can go for Raman, NMR, etc. So these are the very commonly used chemical characterization techniques. And if, one of the highly researched aspects in material science and chemical engineering, and also people from the physics and chemistry background, are electrochemical devices like batteries, supercapacitors, hydrogen storage, hydrogen evolution, hydrogen evolution reactions, oxygen evolution, reactions, which is basically HER, OER, etc. So these are the few things that people from physics and chemistry, material science, chemical engineering, all these people are regularly working on these aspects. So these kinds of characterization techniques, just called the electrochemical characterization techniques, is also being widely used in current state of research. So in electrochemical characterization, the basic techniques that are regularly followed are cyclic voltammetry, charge discharge, galvanostatic charge discharge, and electrochemical impedance spectroscopy, EIS. Okay. The next question what we discussed was what are crystalline and amorphous material? So basically, a crystalline material is a material where there is a regular and periodic arrangement of atoms. Whereas in amorphous material, there is no such regular arrangement of atoms or molecules. You can see from this figure, the first one is an example for crystalline, and you can see there is a well-ordered arrangement. You can see the atoms, we count this 1, 2, 3, 4, 5, 6, is has a neighbor, maybe 6, 7, 8, 9, 10, 11, and you can see there's a proper arrangement one after other without any defects or any other thing. So this is a very well properly arranged system of atoms, and this is an example for crystalline material. Whereas if you go for amorphous, you can see that there is no regular arrangement, like mostly the particles would be arranged in a very random manner, and this is an example for amorphous material. Now, since we are discussing about the characterization technique, let me just tell you how will the for example, an X-ray diffraction pattern, XRD pattern, for an crystalline material, we expect it to be straight lines with a very strong peaks at some particular value of angle. You can have intensity on the y-axis and angle to theta on the x-axis. This is basically XRD plot, and you can get sharp peaks at regular, not on the regular, at very distinct angles. But for example, in an amorphous material, here the how the intensity varies is not as of a strong peak, but it will be in a kind of distribution. So it will be something like this. This is for amorphous. So we cannot see any sharp peaks for amorphous materials. Okay, so an example for crystalline is NaCl, and for NaCl we can have regular arrangement, regular proper sharp peaks with arbitrary intensity on y-axis and with theta on x-axis. Yeah, so this is a very basic and fundamental classification of materials. Now, what are nanomaterials? So nanomaterials are a class of materials where one of, like, usually we talk with 3 dimensions, x, y, and z. So if one of the dimension of a material, say either x, y, or z, has its value or length less than 100 nanometer. Say if x has a value 100 nanometers and y maybe 100 nanometer, y has 110 nanometer, y has a length 200 nanometer, but z has a length 50 nanometer. So you can see here that at least one of the dimension has its value less than 100 nanometer. Then this kind of a material is called a nanomaterial. So this nanomaterial behave very differently from bulk. Their characteristics vary very differently from that of their bulk properties. For example, if you are having a material, and there we can have their bulk as well as their nano form, and these two will behave very differently at different conditions. So in order to get information about or in order to have use them for very particular applications, people will go to these nanomaterials and they get different properties that may not be available in their bulk form. So basically, we can show them in pictorially that there are basically 3 types of nanomaterial: 2D, 1D, and 0D. So if you have a material, say like from this figure, we can say this is Z, this is Y, and this is Z. If all the three dimensions are greater than 100 nanometers, then this is a bud material. Now suppose if we reduce this Z axis such that this Z becomes less than 100 nanometer, then we get such a structure which is like a sheet-like structure with Z-axis less than 100 nanometer and the other X and Y directions greater than 100 nanometer. So this will correspond to a two-dimensional material. An example for a two-dimensional material is graphene. So yeah, this is an example for 2D structure. Now if we are having a material with two of its sides like say Z and Y direction has been in a form such that they are less than 100 nanometer, or we can say they are in the range 1 to 100 nanometer. X in the 1 to nanometer, then we can get this kind of a rod-like structure, and this is an example for 1D material. Okay, so 1D material. So in 2D material, we can say that one of its side is having its dimension less than 100 nanometer. In 1D material, we can say two dimensions are less than 100 nanometer. Whereas in 0D material, all the three directions you can see from here, X, Z, X, and Y have their values in the range 1 to 100 nanometers. So this would correspond to a 0D material. An example for 0D material are quantum dots. Quantum dots. For example, we can have carbon quantum dots. Carbon quantum dots. It's also called CQDs. This CQDs has tremendous applications in various aspects like ranging from sensors to other applications. So generally this carbon won't be showing many of its properties when it is in its bulk form, but whereas it shows those properties very much when it becomes a carbon quantum dots. So people use this for many tailored applications, and that yeah, this is also so these people make this carbon quantum dots from very for various applications, from sensors to electronics devices, etc. Now, the other two general class of materials that material scientists or chemical engineers regularly deal with are alloys and intermetallic compounds. An alloy is a homogeneous combination of two metals, whereas an intermetallic compound is a combination of two metals at a very proper stoichiometric ratio. Now, what was ceramics? Ceramics is another class of material that is you very have an application on many different aspects. Here what we do is we treat many materials like clay at a very high temperature, resulting in a material that is brittle, that is hard, that is thermally insulating, that is electrically insulating, etc. Some major identity of this ceramic is its treatment with higher temperature. So, so that makes all these handles are very good applications. For example, when something is quickly insulating, that can be act as insulator for electric devices. So yeah, ceramics are also having many applications. Like recently, ceramics are also being started using in mobile phones as they are very hard materials, and that makes these mobile phones much more durable, etc. And the other kinds of materials are polymers. Polymers is a combination of is a long chain of materials. For example, if of same monomers. For example, if you have a monomer which is like A, P something, and once if this is getting repeated for a very long chain, then we call this as a polymer. So polymer is a long chain of basic chemical units called monomers. So these polymers have its own uses in many applications. Now there are polymer batteries, polymer-based batteries, There are polymer-based electronics, polymer-based electronics, and even in other engineering fields such as the civil engineering, people have been trying to use these polymers to increase the durability of steels and other things, etc. So, yeah, the polymers are one of the very highly studied materials. So these polymers can be of two types: naturally obtained polymers as well as synthetically obtained polymers. And the naturally obtained polymers are obtained from natural resources, and these synthetic polymers are obtained synthetically. For example, we have this the thing that we regularly use is PVC, polyvinyl chloride. So it is a combination of this vinyl chloride. It's a long chain of vinyl chloride that gives us polyvinyl chloride, which is very much used in pipings and other floorings. So we can have this PVC floorings and all. So this is also one of the very much discussed material. The other question was, what was semiconductor? So semiconductor is a class of material which lies in between conductors and insulators, and they have a band gap. So band gap that is higher than conductors but less than insulators. So the basic diagram is such as is this. Here we can see there is this when we plot the uh, energy levels of a material, then we can have this valence band and conduction band. When the valence band and conduction band overlap with each other, it is basically metals. But in case of insulators, the separation between valence conduction band and the valence band is very high. Conduction band and valence band is very high, such that electrons from valence band cannot go to conduction band even if some external energy is provided. So this band gap, which is denoted by Eg, is very high. Now there is another class of material which is called the semiconductor, where the conduction band and the valence band separation is higher than that of a material. Like they are not overlapping with each other, but they are not high as of that of a insulator. And here with by providing some external potential, the electrons from the valence band can actually reach the conduction band, and this can give us many exciting properties, and that can be used that has been used in the electronic revolution. So all the electronic devices we currently use are basically made of these semiconductors, and we can tune this band gap Eg by doping it accordingly, either doping it by an n-type material where the number of electrons are higher, or we are or with a p-type material. So this, by doping these two with these two materials, we can actually tune the band gap and then use it for various applications. For example, if you're using a material for to use a material as a solar panel material, then it should have a specific band gap value. If that is higher than that of this band gap value, if that material is having a higher value than this required energy band gap, then that cannot be used as a solar panel, solar material. Similarly, if you want to use build a material for emitting red color light material, an LED material, that emit red color, and the corresponding band gap should be of a specific value, or else we won't get a required output, that is the red line. So we tune this band gap in such a way by doping it with certain materials and controlling this EG to get specific band gap values. So these are basically the semiconductors. Now, the major type of energy storage devices, actually this was electrical energy storage technologies. So here in this lecture, also some mainly discuss about the electrical storage technologies. So yeah, if we are talking about energy storage technology, energy can be stored in a variety of manner, ranging from mechanical storage to thermal storage to electrical storage to electrochemical storage, etc. Of the electrochemical storage kind of technology, the three main kinds of storage technologies are fuel cells, batteries, and supercapacitors. Okay, so we have seen earlier also. Now I can talk about record plot also. So in record plot, from the record plot, you can see fuel cells are having very high energy densities, whereas supercapacitors are having very high power densities, and batteries lies here. Here this is actually this is capacitors, and this is batteries. This is fuel cell, whereas supercapacitor are going to a range where somewhat here with both higher uh, energy density than capacitor and higher power density than battery. So this is energy density. This is power density. Okay, so these are the basic energy storage technologies. Now, yeah, once again talking about this recon plot. Recon plot is one of the very commonly discussed plot one in terms of this um, in terms of energy storage technologies. So here we actually plot between two values. One is energy density and the other is power density. So in the x-axis, we'll be having power density, and in the y-axis, we'll be having energy density. So each point in this plot would give us information about how the device performs, the energy storage device performs. Like at this particular level, we can say we can get an idea that how much will be the power energy, how much will be the energy it can store versus how fast that energy can actually be extracted from this material. For example, you're having a device, say X device. So this is a device, say X device. So it can store maybe this is a battery, and it can store X amount of energy, and the power output can be 5. Basically, it means that yeah, let me go forward, then I can explain more. For example, with fuel cell is having a very high energy density, as you can see. This means that fuel cells can store very high values of energy, whereas you can see this capacitor, it is having a very high power density. So this means that it can deliver power very faster. It means that you are yeah, so actually we need to go forward is in this pathway where we can get higher energy densities as well as higher power densities. Now, the major differences between batteries and supercapacitor. The major difference between the batteries and supercapacitor primarily comes from their charge storage mechanism. Charge storage mechanism. That is, in batteries, charge is being stored via redox reactions, whereas in supercapacitor, the charges are basically stored with the arrangement of the arrangement of the charge particles. Also, in batteries, generally have very high capacity values, and whereas the life cycle of batteries are lesser. Whereas in uh, case of capacitors or supercapacitors, they have very high power density, or they have lower capacity, high power density, low energy density, and they have a very lower capacitance value. But the life cycles of these supercapacitors are life 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 cycle of the supercapacitors are generally very high. Okay, so this are the basic difference between the batteries and supercapacitor, and you can see the schematic. From this schematic, you can see the first one shows the schematic of a typical electrical double layer capacitor, and the other figure B shows a typical structure of a lithium-ion battery with the graphite anode and cathode. Here the cathode material is taken as lithium cobalt oxide. So during charging, this lithium from this cathode will go towards this anode, and that gets stored between the anode between the that will get intercalated to this graphite, and during discharge they travel back. So there is a regular movement of ions, charged ions in the batteries, whereas here the particles, like the positive material, would get accumulated near to the negative electrode, and the negative ions would get accumulated near the positive electrode, and this would give this smaller uh, distance of separation. For example, we know epsilon 0, epsilon r, a by d capacitors can be calculated by this step. And if the d is very small, where d is the separation of two charges, positive and negative, and if this charge separation d, if this is very small, the value of c would go higher, and the energy can be calculated half cv square. And if c is higher, then d is obviously higher. So the basic working of a supercapacitor is by controlling this distance and making this distance to very smaller unit, so that the value of capacity increases, thereby increasing the value of energy. So this is the major difference between a capacitor and a supercapacitor. Now, name a few beyond lithium energy storage technologies. Now, the scientists are like lithium has various demerits nowadays. Nowadays, lithium has its own basic demerits, like the availability of lithium on Earth surface is very low, and that the distribution of this uh, lithium uh, uh, is also very limited, and only few countries have access to lithium sources, and this causes many geopolitical issues. So people are going looking for to other storage technologies that is free from lithium and using other more eco-friendlier. For example, if you consider the case of India, India has a uh, very little, or say very little source of lithium, and so India has to depend on other countries to get quality. Uh, Very little, or in the sense there is no lithium depositions in India, almost no depositions in India. So the India has to depend on other countries if India wishes to make lithium-based batteries. So instead, if we go for other materials where India is rich, for example, India is rich in bauxite, or we have the sodium is also very much available in India. So if we go for such kind of technologies, we can be more useful. So there are many researchers, like there are sodium-based batteries, there are aluminum-based batteries, there are potassium-based batteries. People are also going for calcium-based batteries, magnesium-based batteries, etc. But still, lithium rules the market because the size of the lithium ion is very small when compared to sodium and when compared to aluminum. So this smaller size makes lithium very much useful in batteries so that they can intercalate into the anode, and how that destroys the structure of the anode material is very less because this has a very smaller structure, whereas sodium comparatively having much higher structure can damage the anode electrode material due to after continuous charging and discharging. And again, this is very much higher for aluminum. So people are working on different strategies to increase the performance of sodium, aluminum, potassium, calcium, etc. based batteries. Now, what are supercapacitor and what are the basic capacitors? I've already explained you what is supercapacitor. Supercapacitor is a kind of storage technology. It's a kind of storage technology that has depends on the charge, like how the charges are arranged. So here we will be, so here based on the charge storage mechanism, we can have electrical double die capacitor, we can have pseudo capacitor, we can have hybrid type capacitors. So in the electrical double die capacitor, the that we have an electrode, and this electrode would be having specific charge set positive, and we have ions in the electrolyte, which is, so there are two electrodes, in between is filled by electrolyte, and electrolyte can have two ions, positive ions and negative ions. So near to this positive electrode there will be a regular arrangement of negative ions, and this distance would be very small, and this generally corresponds to a electrical double die capacitor. Whereas in pseudo capacitor, there will be Faraday reactions, and that would lead to the storage of energy. And in a hybrid capacitor is a combination of EDLC type supercapacitors and pseudo supercapacitor. Now, based on the device fabrication, we can get two kinds of supercapacitor. One is symmetric, whether both the electrodes are made of same material, whereas in asymmetric, the electrodes are made of different materials. Now, the techniques that is used to analyze the surface area and pore size is called dash. So that technique is called PET, which depends on some gas, generally nitrogen, to get to understand what is the absorption of nitrogen into the material surface, by which we can get the information about the surface area and the size of the pores within the material. So these two are the two generally studied parameters using BET, and BET start, and the BET stands for Brunner, emit, and emit and Teller. So this technique is named after the scientist to develop the theory behind this technique, and we will be discussing about, sir will be discussing about this techniques in a much detailed manner in upcoming lectures. So yeah, so this is PET and the dash. So the dash function is used in the particle size analyzer to calculate the particle size distribution. So the answer for this is autocorrelation function. So autocorrelation function is a function that is generally used in a particle size analyzer to get the idea of how particles are distributed. How particle distributed, that in this order of, like, considering their size distributed within the material. So this information can be obtained by calculating autocorrelation function. So we'll be learning more about this in the upcoming lectures. Now, the other regularly used technique is thermogravimetric analysis, which this would give. So the question here is the thermogravimetric analysis measure dash as a function of dash. So basically thermogravimetric analysis measures the change in the mass of a material with a change in the temperature. Yeah, so this is the required answer. Now going further, chemistry option basic measures dash and dash. So basically chemistry option is used to measure the metal dispersion and the active metal area. So metal dispersion is basically the ratio of number of surface atoms to that of number of total atoms. So this is metal dispersion, and active metal surface area is the area that is available for chemical reactions. Now, the next question was, the dash technique can be used to calculate the quantitative determination of transition metal ions and the battery of the material. So the answer for this was UV visible spectroscopy. So yeah, I was explaining you with an example of Cr2O3. Suppose you're having the material Cr2O3 and you need to calculate the band gap of this. So you perform this, you can perform this UV visible spectroscopy to get the band gap for this. So once again, we'll be discussing this in detail in further lectures. Now, the dash technique can be used to study the molecular structures and the interaction of metal ions. So the answer for this is the Raman spectroscopy. So Raman spectroscopy is a technique that we basically use to understand the molecular structure, see how different functional groups are attached, and we can get many ideas about the basic structure of the molecule. Now, yeah, we have discussed this in a very much detail. Yeah. So the question here that was asked was, what are the three different spectroscopic techniques that is regularly used by in material science or chemical engineering? So, and they are XRD, which not XRD, I'm sorry. They are XPS, which stands for X-ray photon spectroscopy, and XFS, XRF, which stands for X-ray fluorescence spectroscopy, and the other one was AES, exposure electron spectroscopy. X-ray XPS is generally used to understand the surface chemical composition of the material, whereas XRF and AES can be used to understand the bulk composition of the material. Now, the next question was, the dash parameter is measured in a NMR spectroscopy, and the answer was chemical shift. So, yeah, we measure this chemical shift with respect to, measure this chemical shift, and that can be used to understand what is the chemical composition of the material. Now, the NMR spectroscopy is used to determine dash. So there are many parameters that can be determined by NMR spectroscopy, and some of the commonly used are NMR is generally used to understand basically the quality of the material, like what is the composition, and we can get the information. We can analyze the mixture composition of the material. We can get the structure of the material, etc. Now, and now the question was, the SEM images shows dash and the TEM images shows dash. SEM images that generally shows the topology or surface morphology, whereas the TEM images shows the internal structures. So if from these figures we can see that the SEM images clearly give us information about how what is the morphology and how these structures actually seen are visible from outside. But we do not get an idea about their internal structure. For example, see here, these are very hard spheres. So these are hard spheres. So from outside we can see that they are sphere, but to get to know how their internal structure is, we can perform a TEM experiment, and we can see the inside is also uniformly filled. Whereas you can go for this kind of structures where from outside we can see it as regular hard spheres, but when we look it through TEM, we can see that actually their inside is hollow. The similar can be observed from this and this. You can see that from outside it may seems to be hard material, but actually from inside they are hollow. So these kinds of materials have their use in various applications ranging from electrochemical energy storage devices to sensors to other different applications. So it can also reveal the wonderful structures that is possible in the microscale and nanoscale. For example, from this figure, you can see there is a cactus like morphology that has been obtained. So this is an example for CR203. CR203 is having this cactus like morphology. It is having some protrusion, some of the surface, and that can lead to proper channel for the electrolyte flow, and that can cause an increased performance. So all this can be analyzed through these SEM images. And there is another. You can also go for this type. See, there is a rose like arrangement, and there is a plate like arrangement, and there is a tube like arrangement. So all these surface morphologies can be obtained from SEM images. And to understand the internal arrangement of the atom, and go for TEM image. That and the 23rd question was the working voltage window. What of the supercapacitors can be found using? The answer was cyclic voltammetry or CV. So the basic electrochemical characterization techniques are linear voltammetry, cyclic voltammetry, galvanometry, static charge discharge, electrochemical impedance spectroscopy. So out of this, the cyclic voltammetry, or it's generally called CV technique, is used to understand about the working voltage window in a supercapacitor. This working voltage window would determine the energy storage capability of the supercapacitor. So it is very important parameter when considering when fabricating a supercapacitor. Now, the last question was the not the last, the 24th question was what does the EIS measures? The EIS stands for electrochemical impedance spectroscopy. So impedance is generally the resistance when we talk about AC circuit. So if you have a device, if you need to calculate the internal resistance or its resistance to AC circuit, we generally does its EIS measurement, and then we get it get the its resistance to the AC current. Now the last question that we discussed was dash are defined as a material that contains a mixture of two or more phases that are chemically different and are separated by an interface. So this answer for this was composite. So I have also discussed an example of graphene and moisture composite, and here we can see that the moisture and graphene are not chemically connected, but they are separated by an interface, and these two are of two phases. And these kinds of material can have many applications. As I said, moisture generally has lower conductivity, but when it is combined with graphene, it can have very high conductivities. So yeah, basically the conductivity of the moisture can be increased by graphene, by making graphene and moisture composite. Yeah. So these are the currently topics that I was interested to discuss with you. So thank you for your kind attention, and we would uh, we would again meet in the next week. And if you guys have any further questions, you can ask. So if you don't have any further questions, then let us stop for today. And we'll meet on next week with further questions. Thank you.